Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillahirrahmanirrahim. Problem 8.2. So the statement of problem is that solve problem 8.1 assuming P is equal to 22.5 kips and A is equal to 20 inch. So this problem is same as problem 8.1, but the value of P and A is now changed. So I am not going to solve it. I will just go through this problem. Only the value have been changed. Clear? So have a look on this problem. So statement is given that W10 by 39 rolled steel beam with load P is 22.5 kips, given A is equal to this A is 20 inch and this distance BC is 10 feet, which in inch is equal to 120 inch. Also it is given that allowable stress is 18 ksi. So you have to find the maximum value of normal stress in the beam, which is sigma max at the top of the flange. Clear? And in part B it is given that maximum value of principal stress sigma max at the junction of flange and web. So this is the cross section of the beam. So you can see this portion is known as flange, this portion is known as web, and the point or the line where the flange and web meets is known as flange web junction. Clear? So you have to find the principal stress at this junction, and in part 3 it is given whether the specified shape is acceptable as far these two stresses are concerned. So we will then check based on sigma max and principal stress. We will also check that whether this specification is acceptable or not. The first step in solving this problem is to find the reaction forces at point A and D. Clear? So we will draw the free body diagram of this beam that is already done over here. So you can see at point A the reaction force is RA, at point D the reaction force is RD. P loads is applied at point B and C, and the distance is also mentioned over here. Clear? So by using the first equilibrium condition, that sum of all forces along y direction is equal to 0, so you can see RA is upward, so RA minus P plus RD is equal to 0. So RA plus RD will be equal to 2P, or we can write RA in term of P and D, which is this one. So RA is equal to 2P minus RD. So this is the first equation. Now we can apply the second condition of equilibrium, that is sum of all moment about point B is equal to 0. You can take the summation of moment at any point equal to 0. You can take A, B, C and D. I have taken at point B. So when you apply this condition, so you can see at point B, the only at point B this force RA is producing moment about point B, and the moment will be RA into 20. So my RA into 20, a negative sign shows that clockwise rotation is negative, so minus 20 RA. Similarly at point B, the another force which is producing moment is P into perpendicular distance 120, and it is also producing clockwise. Clear? So this is again minus 120 P in clockwise direction. The other force which is producing moment about point B is RD. So RD into perpendicular distance is 140. So clear? So this is 140. Clear? So 140 RD is equal to 0. Now you have to put the value of RA over here, and RA is equal to 2P minus RD. Clear? And you can calculate it. At the end you will get RD is equal to P, and you can put the value of RD over here, so you will get RA as well equal to P, and P is given as 22.5 ksi. Now we have reaction forces. The next step is to find the maximum stresses, and maximum stress is equal to maximum bending moment divided by Sx, which is section modulus. So if you have this figure of the free body diagram of the beam, you have this is RA. Clear? This is equal to RD. Clear? So you can draw the shear force and bending moment. So from shear force and bending moment, we will get the maximum shear force and bending moment. So you can see here RA is equal to P, which is 22.5. So let this point is 22.5. So from this point till this point, here in between this section, this will be P, which is 22.5. Now at this point B, clear, this is plus 22 and this is minus 22. So at this point B is, shear force will be 0. And again you can see between point B and C there is no force, so shear force will be 0. Clear? But at point C there is a load of minus 22.5, so it will go down. So this will be your shear force diagram for the beam. Now we will draw the bending moment diagram. For bending moment, you can see from point A to B. Clear? This is the shear force diagram, and the area under the shear force diagram is bending moment. So you can see this is a rectangular, so area of rectangle is 22.5 multiplied by 20, which will give you 450 kips into inch. So you have to locate at point B 450, and since this is a horizontal line or 0 degree line, so moment equation or moment will be 1 degree higher. So again this is positive, so the bending moment will be a straight line. Clear? Now you can see there is no moment, no shear force, so the moment will be straight one. Clear? And here the moment is again a area under the shear force diagram, and it will be minus 450. So this is plus 450 and minus 450 will be equal to 0. So this will be this straight line will be a bending moment diagram for this portion C and D. Since this shear force is negative, so the bending moment will be minus 450 and this will be downward. So from this we conclude that we have a maximum shear force of 22.5 kips, and from bending moment we have maximum bending moment 450 kips into inch. Clear? You have this value, you do not have SX. So from the W10 by 39, so if you go at the appendix C of the book Mechanics of Material by Baer and Johnston, you will find the properties of this rolled steel. So from that you can get the height of the beam, the breadth of the flange, clear, the thickness of the flange, the thickness of web, the second moment of inertia, section modulus. So again I have drawn and I have explained it in problem 8.1. So if you look at the beam, this is D, so D value is this one. This is thickness of flange, which is this one. This is the thickness of web, which is this one. Clear? And the flange breadth is equal to this one. Clear? 7.99, and all the values are given. So if you haven't watched the problem 8.1, I will suggest you to go through and you will easily understand what is going on. Clear? So if this is the beam, this is total height D, clear, and this is the from center to the outermost surface, clear, this distance is C, and from center to the junction point, this is YB. C is equal to half of D, which is this one, and YB is equal to C minus this thickness of the flange. So if you subtract this thickness, clear, from this C, so you will get this YB, clear, not this. This is YF, this is something else. So from C minus this thickness will YB, clear. Now you have the section modulus from here and you have bending moment from here, so you can put the put the value in here. Bending moment is 450, section modulus 42.5, which will give you 10.69. Again, this is the maximum stress at the outside of the flange. Now in second part, it is given to find out the stress at the junction of web and flange. So this is the junction, or this is the point B. So you can see this is the point B. You have to find the principal stresses at this junction. So for principal stresses, you know that we have formula sigma 1 comma sigma 2 is equal to sigma average plus minus r, and this r is equal to this value. Here you will need the normal stresses and shear stresses. So first we will find the normal stresses at point B are the junction, and the shear stresses. Once we have normal stress and shear stress, so you can use it in the formula of principal stresses and you can calculate. So let's move toward finding the normal stress at this junction point. So this stress at point B will be equal to the ratio of YB over YC. What is YB? YB is distance from neutral axis to the junction point, and C is the distance from neutral axis to the outermost surface. So YB over YC into sigma max will yield you sigma B. So we have put the value and we have calculated sigma B, which is 9.55. Again, this is explained thoroughly in problem 8.1, but I am again explaining it. Now you have this normal stresses, and we know that we need shear stresses at this junction point as well. So formula for shear stress is V max Q divided by I into thickness of web. We have V max from the shear force diagram. We do not have Q. We have I, second moment of inertia, given from the property. We have thickness of web. So we will find the Q, which is the first moment of area about the neutral axis. And we know that this Q is equal to area into YF. So this is area of flange into YF. Area of flange is equal to breadth of flange into thickness of flange. When you multiply both, so you will get the area of flange. Clear? Now what is YF? YF is, this is the flange. Clear? So you can see the flange. So if the center of flange is this one, so distance from neutral axis to the center of flange will be equal to YF. And this YF is equal to YB, this YB, and this distance. And this distance is thickness of flange divided by 2. So YF will be equal to YB plus TF over 2. Again, it is written. So when you put the value of TF and YB, you will get YF. Now you have YF and AF, you can multiply it, so you will get the first moment of inertia about the neutral axis. Now put the value of Q, V, I and TW in this formula, so you will get the shear stress at the junction point. Clear? Now we have normal stress and shear stress at junction point. The normal stress is sigma B and the shear stress is 6. This is the oldest value of problem, 6.79. So you can put the values clear in this formula. So for principal stresses, we know that sigma 1 comma sigma 2 is equal to sigma average plus R. We need the maximum value, so we will take the plus 1. Clear? So sigma 1 will be equal to sigma average plus R. And we know that sigma average is equal to sigma x plus sigma y divided by 2. So you can see here you have only single stress, that is sigma B, and sigma y is equal to 0. Sigma average will become equal to sigma B over 2. Clear? So sigma average is equal to sigma 1 is equal to sigma average plus sigma average square plus tau of xy square. So sigma average is sigma B over 2 and tau of xy square is 6.79. So if you calculate it, you will get the principal stress at the junction, which is 13.08. So this was the second part of the problem. Now in third part, it was given that to check whether the beam is acceptable or not. So what we have is the sigma 1, which is the principal stress at the junction. So it should be less than sigma allowable for acceptable beam or for safe design. So from here you have sigma 1, which is 13.08 ksi. Clear? And from the given data, sigma allowable is 18 ksi. So you can see sigma allowable is 18 ksi. Clear? This is the value. So you can see sigma 1 is less than, our principal stresses is less than allowable stress. Clear? So hence we recommend that W10 by 39 is acceptable under the given loading condition. I hope you have now a clear idea how to solve this type of problems. Thank you for watching.